Hi, I'm John Stock. I run the USGS National Innovation Center. I'm pleased that my agency is sponsoring the Waters of the United States FDL Challenge this summer. I'm going to take a few moments to describe the USGS to those of you who may not know us, and then I'll tell you why we think this challenge is so important, not just to us, but to countries around the world. The U.S. Geological Survey was born in 1879. Since then, we've developed the facts and forecasts our nation needs for its lands, waters, and ecosystems. Our maps and data tell an ever more detailed story of our national assets, like our minerals, soils, waters, and ecology, and our hazards, like earthquakes, floods, volcanoes, and landslides. Our nation uses USGS maps, data, and expertise to make decisions about the natural resources that we use to build infrastructure and commerce, and the things that threaten them. The nation trusts our tools because we provide facts and forecasts without advocacy. In short, we provide knowledge for national action. But we have some gaps in that knowledge. One of those gaps is where are our streams flowing right now? Earth's branching stream networks expand with floods and contract with droughts. There's no one map of our streams. But what if we could map these flowing networks every day, stacking the time series maps over many years? Mapping our daily waters gives us an early warning for where droughts are born, the receding tips of the flowing network. Mapping them over years gives us a map of the impermanence of our waters, showing where to expect water and where not to. This would be a fundamentally new map, one that has never been made at scale before, and one that will have huge impacts on water resource use around the world. Today, you're going to see a talented group of data scientists explore our ability to augment human mapping by applying AI to high-resolution satellite imagery. USGS scientists from our water mission, our National Geospatial Program, and our National Land Imaging Program have been working hard over the last months to provide the training data for this effort. This partnership happened because of the generosity of our colleagues at NASA, Maxar, Planet, SETI, and Trillium. I look forward to exploring how USGS will use these models as we pursue the goal of mapping our nation's streams in real time. Thank you.
Hello and welcome to today's digital showcase. We are the Waters of the United States team, short VOTUS. While we already heard of FDL challenges today related to floods and their effects, one of VOTUS's goals is to assess where such excesses or shortages of water come from in the first place. Our team consists of researcher Dolores Garcia, Gonzalo Mateo, me, Hannes Bernhard, Ron Hagensieger, as well as ML lead Freddy Kalaitzis, super mentor Guy Schumann, USGS contact Jonathan Stocks, domain lead Kevin Dobbs, and ML support Ignacio Lopez. We also want to specifically thank our sponsors, Planet, USGS, Google Cloud, without whose processing capabilities, storage capabilities, and data, this project would not have been possible. The current framework for the mapped US stream network is based on mapping campaigns conducted in the mid-20th century, that is 60 to 70 years ago, and based only on a single set of images. From an ecological, sociological, economic, and regulatory standpoint, more information is needed on the time-varying characteristics and categorization of streams in the network. The VOTUS challenge is focused on using modern methods and a range of geospatial data to refine and update the categorization and characterization of the streams at continental scales. The challenge asks the question, can we use machine learning on these satellite observations in combination with modern high-resolution terrain data and other ancillary data to fortify the sparse observations currently available via stream gauges? What about those stream gauges, though? While the US stream gauge network is one of the densest and most comprehensive of its kind in the world, it still only represents point sampled at discrete locations. Although this network covers major streams across the US, supporting science, disaster response planning, and most importantly, policy guidance, these observations only offer small fractions and cover only a small fraction of the US stream network. Indeed, the vast majority of the remaining streams in red, or 97% of streams in themselves, missing many small streams not in the map at all, have no observed data on frequency of flow or current state, and have functional characterizations that have not been updated in over half a century. Moreover, the amount of streams missing from the current data set represent a huge unknown volume of water whose eventual assessment is required for reliable drought and flood prediction in the future. In the next section, we will outline the data and methods And we have used over 4 study areas to explore new methods that can be brought to bear on the VODAS challenge.
So now we have access to always improving satellite geometry, but it still has limitations. I'm going to talk to you about the different satellite data providers. So Landsat and Sentinel are the standard images used for wide area mapping. They offer a total of 8 images per month and 10 to 30 meter resolution. However, these low resolutions make them insufficient for mapping more streams. Another dataset available comes from Maxar. These images offer extremely high resolution images that could be sufficient to map most rivers. But these images are limited and on demand, so we can use them for continuous mapping. So until now, we had these 2 datasets available. And in 2014, the company Planet started populating the large constellation of high resolution, rapid coverage satellites. This constellation provides 30 images per month at 3 meter resolution. So to sum it up, there is Planet providing 1 image per day at intermediate resolution, and Maxar providing 1 image but at very high resolution. So our approach is to take advantage of the different sensors having different resolution, so Planet with 1 image per day and Maxar with a very high resolution, and also to leverage the elevation map provided by the USGS that has the information about where the valleys are and therefore where we might observe water. And what we have observed is that excluding one of these data sets greatly reduces our ability to identify streams. So we use all this data to train a machine learning model to obtain water detection map on each image as an output and study how well we can map the water presence on the surface as a function of time based on this novel high-resolution imagery. So more specifically, let me tell you how our algorithm works. So we have a multi-day planet time series, and this fused in a single representation using 3D convolutions. Now, the other input is the elevation data at a different resolution. We downsample it to the same size as the planet representation and fuse it. We'd like to obtain as an output of the model an image representing the water detection per pixel. This is called a semantic segmentation problem. For this, we input this user representation to a modified unit, a state-of-the-art architecture for semantic segmentation problems. Now, to train our model, we need to give it some examples of what is wet and what is dry. But this is complicated with the planet images. It would be even complicated for a human. So this is where the Maxar images that we're talking about at higher resolutions come in. For our challenge, the USGS, one of our partners, and us use Maxar images to create an extensive data set of labeled polygons covering many small areas, many small and larger streams. Those are at 0.5 meter resolution, which allows to draw more precise labels. And we apply those then to the planet images to train our model on. And this is what allows us to obtain a high resolution output that until now wasn't available at daily predictions. And we call this model the 3D multi-headed unit.
So what has VODAS achieved? In the background, you see a sample of our water detection map based on high-resolution Maxar in one of our areas of interest, South Dakota. You easily recognize the granularity and detail we achieved. On the side panel, you see a roughly 8 kilometer wide sample of how we improved over the state-of-the-art established by FDL. Attesting to the veracity of our products, we reproduced all detections made by FDL, but also offer many more small streams and also standing bodies of water that come out in great detail in our data. Daily planet imagery also allows wet pixel identification over time. While shadows cast from the walls of many small canyons still cause some false positives in the scene, variability is greatest along the smaller tributaries of the scene, as well as along the banks of the large river, which is exactly what we would expect. Such time series allow for categorizing each stream to update and expand the National Hydrography dataset, as well as to assess surface runoff over time in correlation to precipitation, and an array of other parameters to establish more precise forecast models. From this an online interface akin to Google Maps can be developed that could visualize real-time daily data, including the respective wet pixel identification and derived predictions. Now, to wrap up, the waters of the United States, particularly streams, are a matter of place and time. The already mentioned National Hydrographic Dataset in conjunction with the National Stream Gauge Network aim to map and monitor the rivers of the US and therefore assess water availability. However, both suffer from inherent problems, with the dataset being outdated, incomplete, and difficult to update. The Stream Gauge Network, with its finite number of stations, is costly to maintain and expand, and thus only captures a fraction of stream activity in the US. The VODIS approach offers a solution to these problems by utilizing remote sensing data of high temporal and spatial resolution. Machine learning allows for automated mapping to refine a hydrographic dataset, and daily coverage enables verification and updating of stream categorizations therein, as well as to assess stream activity over extended periods of time in areas that are optically cooperative. This will enable regional predictions of water availability, the importance of which become clear once we consider that in the US, droughts and floods have caused an estimated $236 and $126 billion worth of damages, respectively, since 1980, second only to hurricanes. Thank you.
Thank you so much to our Waters of the United States team. So I'm going to invite the whole team to join us back, as well as our panelists, for our last question. So for this question, I'd really like to know what stood out for you in that presentation. And to kick us off, I'd love to go to Aaron.
Yeah. So beyond the number of stream gauges in the East versus the West, again, policy implications because of how contentious water policy related to water quantity, not to mention water, there was how much water quantity, not to mention water quality, how contentious that is in the US right now. So yeah, this great importance and applicability.
Great, thank you, Aaron. And now we're on to Rodney.
So the one thing that really stood out to me as part of this presentation was clearly the more qualitative visualization, where you could see the dramatic improvement in identification of the stream from the state of the art to what this team was able to come to as part of their work this summer. One sort of half-baked idea that struck me when I was thinking about ultimately what the goal of this team was, is identification of these streams, was the first team's presentation on Moon for Good, and their attempt to actually map out sources of water. And now, maybe many generations from now, when we have a sustained lunar presence, this same sort of capability could be transferred to support a similar sort of philosophical and conceptual approach about attempting to recruit these same capabilities, not just for water in the United States and on Earth, but water on the Moon.
Thanks, Rodney. That's really interesting. I think that would be a really unique capability with this team could help out with. And Scott, closing us out.
So in wrapping it up, I think, Sarah, what we've seen a theme here today, which is you've got this fusion of regular science with AI at a scale of cloud doing amazing things. And here in general, the theme here today also is that water is perhaps the most scarce and valuable resource for human existence. And now we have two teams that are now showing what happens when you marry those two technologies together, and just doing astounding early work. And I encourage them to continue. And I think, as Rodney said, I want to see these on the Moon and within weather forecasts and all over this just needs to be part of life.
Great. Thank you, Scott. And thank you to our panelists and to Team WOTUS. Amazing work. So we're going